I am going to discuss about light matter interaction in waveguide quantum electrodynamic systems, and I will be very kind of simple throughout my talk, so I hope many of you will be able to follow me. So this is my plan of the presentation. So these waveguide QED systems are recent platforms to realize strong light matter interaction for few propagating photons in the absence of any cavity. So this is how it is different from cavity QED setups. So there is no cavity along the propagation of light direction, and we can still have strong light matter interaction. And in this talk, what I am going to discuss, I am going to discuss generation of effective photon-photon interaction using that strong light matter interaction for few photons. So I am going to discuss nonlinear optics in the quantum regime, and I am going to discuss nonlinear optics with few photons, like minimum 2 photons with single atom, and also I will do it for propagating photons, not photons inside the cavity. So this is how I distinguish from many of these presentation. So I will start by giving basics of the waveguide quantum electrodynamic systems. Then I will discuss two theories. One will be many body scattering theory for input photons in Fock state, and another will be this Heisenberg equation or input-output theory for coherent state input. And then I will show, as an application of this effective photon-photon interaction for propagating photons, non-reciprocal light propagation in such system. And finally, I will discuss how to quantify this effective photon-photon interaction using Kier or cos-Kier effect. And we wrote a review article on this topic. So we called it Strongly Interacting Photons in One-Dimensional Continuum. We wrote it in collaboration with Professor Chris Wilson from IQC and Offer Fastenberg from Weizmann Institute. Okay, so as I said, I will be very simple throughout my talk, and as all of you know, photons are elementary particles with zero rest mass and neutral particle also. So then photon-photon scattering in vacuum will be extremely weak. In fact, it has never been observed for optical frequency or lower frequencies. But still we can create effective interaction between single photons in the QED regime by employing strong light matter in coupling inside matter. And for this I will try to introduce a little bit about this light matter coupling, which I am going to use a lot in my theoretical description. So generally light matter interaction is a quantum electrodynamic phenomena with quantum electronic transition associated with some kind of absorption of light or spontaneous emission or stimulated emission of light. So in the case of, let's take absorption, if we have an atom, two-level atom in the ground state and we shine photon, then atom will be excited by absorbing this photon, and if we leave this atom for some time, it will emit photon spontaneously in random direction. So the phase and direction of the emitted photons can be will be random. And then there can be another process for this excited emitter if we shine another photon on it. So then there will be emission of two photons in the direction of incident photon. So I will use these three simple processes to build the theory of the system which I am going to discuss. But before that, I give little bit introduction why waveguide QED was needed or why it was developed kind of. So of course we all know that cavity quantum electrodynamic systems were developed to have strong light matter interaction at the level of few atoms and photons. And in cavity QED, what we do is place a few atoms or one atom inside a cavity made of two mirrors, and their photons interact with this two-level system. We can model like we have a two-level system with transition frequency omega e, and sigma dagger is the transition for ground to excited state, and sigma is the opposite transition, and gamma here is the emission of this excited emitter to modes outside the cavity photon mode. and omega naught is the frequency of this photon mode inside the cavity, and this is within rotating wave approximation or the light matter interaction, which showing here the G is the strength of this light matter interaction, which depends inversely square root of mod volume, so volume inside the cavity, and yeah, I already said A and A dagger are the annihilation or creation operators for the photon mode inside the cavity. Now there will be also loss from this cavity, which is here we model as, let's take kappa, and the strong coupling regime for this light matter interaction will be realized when G, the coupling strength of atom with this photon, is much stronger than kappa or gamma. So this is this cavity QD setup where we can realize strong light matter interaction for few photons and atom, and as you see, as I described, that it depends inversely on the square root of mod volume. Now, what the advantage of another kind of setup which is similar to cavity QD is the solid state version of this one, and we can okay. So by the way, we can have for alkali atoms cavities in optical regime, or for Rydberg atoms which Sanjukta was talking in microwave regime. Even we can have cavities for ions also. Now, advantage of this solid state analog of this cavity QD system is that this mod volume we can control very much using this kind of superconducting transmission line, and we can increase this coupling strength. So we can increase coupling strength between this two-level system, for example, and photon here, and by that increment we can have stronger light matter coupling. So what I am showing here, this is the superconducting transmission line with a central plate made of superconductor and two ground plates, and here in the middle plate has two capacitive gap, which is making this cavity or mirror, and the green one is a superconducting qubit, artificial atom, here like a Cooper pair box, and these red lines are microwave light. Sorry? Yeah, they are mostly superconducting, right? Niobium, for example. Okay, so here is why we are mostly interested in microscopic light matter interaction. Again, following Sanjukta, she was also trying to motivate why we need light matter interaction at the level of few photons and atom, because we want to control photon one by another photon. So we want to have device, all optical devices or gates where we can control one photon by another photon, or the motion of one photon by another photon. And of course, there will be other interest to make interacting photons, because we can then mimic quantum many-body behavior of electrons by light. So that is also one of the interest why we want to have light matter interaction in microscopic domain. And cavity QD, of course, is useful for many of these purposes, but there are few drawbacks of cavity QD. One of them is that if we want to use these photons which is coming out from this cavity, so these photons which are coming out, their bandwidth is determined by the mirrors, and also the photons which are coming out, they are stochastic in nature. So that means, and sorry, another drawback. So these two are drawback, and there is even more fundamental drawback. So let's take, we are using this as quantum gate, and we want to make a network out of this quantum gate. So then what we need these photons to communicate between different gates, but the problem with cavity QD, those coupling itself will be very small for huge network. So quantum networks will be challenging using this cavity QD setup, and that is where free space light matter coupling is useful. Okay, so we can overcome all these challenges in free space, but the problem in free space, in 3D free space, that this coupling strength is relatively weak, because that is why we are using cavity, right? So we are using cavity to increase the light matter coupling. But now if we try to look light matter coupling at the few photon levels in free space, so generally it will be very weak, because again we can go through this theory, like let's take the semi-classical description of light matter interaction can be written in terms of dipole moment and electric field at the dipole moment. So then the scattering cross section or the probability of exciting the atom is determined by sigma by A, where sigma is the atomic scattering cross section and A is the cross section of the light beam transverse direction in the propagation. So now what we can have, like when we can excite one atom with probability 100% is when sigma equal to A. In principle, we can do that even in free space by spatially means by either tidally focusing. So in the case of tidally focusing, we can go to 80%, 85% limit. And in the case of where we can actually create directional dipole wave, so there we can even have theoretically 100%, but practically it is never more than 30% yet in 3D. So that is where this 1D waveguide or free space light matter interaction comes. So what now we are trying to do, we are using this high confinement of propagating light field deeply in the sub-wavelength regime. So that means we are much below the diffraction limit. And also we are using artificial atom which has huge dipole moment. So because of these two advantages in the superconducting circuit as well as in photonic crystal waveguide, one can actually have strong light, this coupling, or which I was saying, this sigma by A strength or ratio almost 100% in this system. In fact, that is what is seen in these two papers. So this Chris Wilson paper as well as paper from Japan, so they have seen almost 99 or 99.9% extinction of the forward extinction of the incident light beam by this setup. So what the setup changing, that gap in the middle plate is removed here. So that is means we are not confining light within cavity, we are having a waveguide which is freely propagating. So there is no confinement along the direction of light propagation. Now I am going to discuss mostly the theory, because where I contribute, and I have not contributed in the experiment part only. So we are going to discuss how to study this atom-photon system in waveguide, mostly how to study this photon-photon interaction in the microscopic regime, not using any kind. Yes, please.
This is your basic Hamiltonian, right?
Yes.
You have this bare Hamiltonian and interaction Hamiltonian, both of them. But you are not coupling the mode. A modes are not coupled to the radiation continuum. Any photon mode, waveguide mode will leak to the continuum.
Yeah, so let me go through the Hamiltonian. I'm sorry, we'll get your answer. Okay, so now this is what the setup mostly people consider in this direction. So we can have two types of setup. One is like a two-level atom side coupled to the waveguide, or we can have a two-level atom direct coupled to the waveguide. So in the first part, which I am going to do for Fock state of input photon in Fock state, I will use this setup, and in the second part, I will use this setup. So I am now giving the Hamiltonian for this problem. So I have free Hamiltonian, which is having these photon modes inside the waveguide and two-level system here. And then we have coupling within these three approximation. Dipole means I have atom size much smaller than wavelength, resonant wavelength of the system. Markovian means this coupling here we are assuming K independent, and rotating wave means we are not taking care any of, means we are doing everything within number or energy conserving interaction. We are dropping all other terms which breaks that excitation conservation. So within this approximation, I am now going to study light propagation. So here in this picture, I am kind of thinking like light is incident from left of this emitter, and in this setup it can be either transmitted this direction or reflected. And for this one, again light is sent from left of this emitter, it can be reflected or transmitted. And what I am going to do, and I am going to show that is what, I am not going to use this description, rather I am going to discuss a real space description of this Hamiltonian, which will show that easy to calculate this many body scattering state. So for that, what I will do, first this dispersion of light can be arbitrary, it can be in fact non-linear in K. So I will do the linearization first. So if I have a dispersion of light, you will see, because here I am not putting V K dependent, that means, but in my theory it will simplify a lot. Yeah, so it depends also on the which system we are talking. So if superconducting transmission line or superconducting system versus photonic crystal is different. So these are mostly in microwave, so gigahertz and 100 of megahertz, let's take. And if we go to optical regime, of course, means quantum dot and photonic, yeah. Yeah, so mostly when I am talking giant within this rotating wave approximation, I will assume, or means this theory is valid when resonant frequency of this two-level system is at least one order higher than the V square, the strength or dissipation from this. Okay. Okay, so now I am going to linearize.
There is a bound part of the spectra, there is a continuum part.
Yeah, so I am coming to that actually. I'm coming one by one. Okay, so as I proposed that I will not deal with the nonlinear dispersion of this waveguide, because that is little complicated in using the means to develop the theory. So we will consider linearization of this waveguide mode. So what I do, I choose a frequency omega naught which is relevant in this problem. So the relevant frequency will be mostly near the transition frequency of the two-level system, and then I will linearize this dispersion near those energy, means near that energy. So I will have a k naught positive mode and minus k naught negative mode, and I will linearize around these two. So when I linearize, I have here now one which is like what you are saying stationary. So this omega naught part is, so I have linearized now, I have omega naught, and then I have Vj k minus k naught, and now I am dividing this, which is for positive wave vector right moving mode, and what is negative wave vector left moving mode. So these modes are my propagating mode, and the part here, this part which I will even, you will see, I will remove that from the problem. So I am mostly interested near omega naught for the propagating modes.
We will discuss later.
Yeah, you can discuss. Okay, sorry. Okay. So now what I am going to do, because I linearize this problem, I get two types of propagating photon modes, right moving modes and left moving modes. And in this description, I have now chiral photons. So photons either moving only right or moving only in the left. They don't talk to each other in the absence of emitter. So the emitter or atom made them couple to each other. So if I shine light in this mode, and if something's propagate in that mode only, we will call that is the transmission, and if it comes from this to the other, means right moving to left moving, we will call it the reflection. So that is how I will define this problem. So I will just skip little bit. So as I said, I made this linearization. I removed this constant k independent terms from this problem by using this total excitation conserved, all these things. And then I get this real space description. So this is the model which we are going to use, or this is the Hamiltonian version, which is for chiral photon modes, right moving or left moving. And this is very popular in condensed matter system, where people talks about chiral channels in topological system and all this bosonization problem. So these chiral modes we are now going to use to develop this many body scattering theory. So what is this many body scattering theory I am going to develop is that, okay, so we are going to use first of all this real space description for Fock state input, and we will use this K space description for coherent state input. And what is this many body scattering theory is that we will choose some input photon mode either in single photon, 2 photon, 3 photons, like different number of photon modes incident in the Fock state, and then we'll develop some unsat scatter state for the outgoing photons, and we will calculate all this unknown amplitude through this theory, and that is where all the difficulties. So let's take for single photon. So if we have a single photon in the right moving channel, I can have, after scattering, 3 different kind of amplitudes. One is excited emitter, which I write by EK. One is right moving photon, which I write by GRX, and another amplitude for left moving photons, which I write by GLX. Similarly, if I have 2 photons and one 2-level system, I can have 5 amplitudes, either 2 right moving photons amplitude, or 1 right moving photons atom in the excited state, 2 left moving photons amplitude atom in the ground state, or 1 right, 1 left moving photon and atom in the ground state, or 1 left moving photons and atom in the ground state. So atom in the excited state. So these are the 5 amplitudes for 2 photon calculation, and similarly there will be more amplitudes for 3 photon calculation. And this calculation was first time done by this group, Sangui Fan from Stanford. So in this paper they did this calculation using some kind of things, again in condensed matter very popular, called Bethe search theory. What he was doing, he was actually not taking any of this intermediate step where atom in excited state. He was mostly looking asymptotic states. And what I did in these papers, actually, I took care of this even intermediate state. And that had some advantage in calculating physical quantities, which I'm going to discuss here. And how do we calculate these amplitudes? We use stationary Schrodinger equation. We calculate, we write some linear differential equation for those unknown amplitudes, and then we use some kind of regularization scheme using this initial condition. We calculate all those amplitudes, and I will show you some of the amplitude also. And once we know those state, we know all scattered state, or whatever nonlinearity is there, what is the photon-photon interaction, everything we know. There is nothing we have to assume or do semi-classical or anything. So this is the actual strength of this kind of theory. We know microscopically what is the scattered state, where is the entanglement, everything. And given that state, we can calculate transmission by calculating expectation of AR dagger AX, AR dagger AR in the outgoing state, or reflection L dagger L in the outgoing state, or 2 photon correlations by second order correlation and all this. So let me show you a little bit how the state looks. So for example, for single photon, this is simple because single photon in the right moving channel where we have incident the photon, it will have only transmission, and if anything goes to left moving, it will be given by reflection amplitude. And transmission amplitude is here like this form, and as you can see, whenever it's resonant condition, photon is perfectly reflected. So a side coupled 2-level system for a waveguide behave as a perfect mirror. And that is actually been seen also. I will show an experimental plot. But the main interesting things come in 2 photon, at least minimum you need 2 photon state. So in the 2 photon state, I have this red part, which is like product form of this single photon state. But in this part, here I have the interesting part, which is called also 2 photon bound state. I will explain you what is this 2 photon bound state. Here I have the center of mass of the 2 photon moving with the total energy like a plane wave, but the relative coordinate is behaving like if the photons start separated between, means distance between photons increases, this contribution will become 0. So that means they are bound in real space. So that is the part which we call 2 photon bound state. So this 2 photon bound state, which is the reason for all the nonlinearity in this problem, even with a single emitter or atom and 2 photons. And this one also actually showing the inelastic scattering from this emitter. Why inelastic? Because 2 photons with incident frequency, let's take Vjk1 and Vjk2, can scatter to different k values. So this is also the which will create fluorescence in this problem. So we are making, as I am saying, that microscopic theory for all of this in this one. And now I don't know if I saw all these things. So these are experiment in this system, and this is transmission reflection, which is here theory, transmission reflection, and this is second order coherence for the transmitted and reflected photons, and these are transmitted and reflected photons second order coherence kind of quantity. So they kind of matches with the early experiment already in 2009 with toroidal cavity, microtoroidal cavity with cesium atoms and taper optical fiber. Okay, so now this direct couple system. So in the direct couple system, as I said, we'll use momentum space Hamiltonian, and we write Heisenberg equation for A, B, AK dagger, BK dagger operator, for sigma, sigma dagger, sigma, all these operators, we time evolve them using Heisenberg equation and use this initial condition that light is incident in a coherent state. And after we evolve this operator, we define the current operator which is given here, and take expectation of this current operator in the incident state and divided by the incident intensity to get the transmission coefficient. Now this transmission coefficient in this system, if we have VL not equal to VR in a direct couple system, so that means the couple here waveguide may be little broader than waveguide this side. So in this case, so these are mostly in superconducting transmission line can be controlled by capacitive coupling, that VL not equal to VR. So now I show you the transmission coefficient for a coherent state from left to right. So if I incident a photon in the left, from the left of the emitter, so this is the transmission from left to right, and this expression will be symmetric if I can drop this part, because this capital gamma T is the total dissipation gamma L and gamma R, where gamma L, gamma R are the dissipation left in the left and right side, and omega L is the Rabi frequency. So this nonlinear part, when we drop this expression TLR, is symmetric under gamma L, gamma R switch. But when we have this nonlinear part, this expression is not symmetric under gamma L, gamma R switch. That means if we sign in this setup, light from the left to right, the transmission is different from if we sign the light from right to left. So light here for any nonlinear regime, means any which is more than single photon regime, will propagate in one direction but will not propagate in another other direction. So this I proposed in this paper actually, and it was yeah, it's how much it can do, means what is the let's take efficiency of this one. So that itself in my theory I can change, means make almost 100%, but this experiment which realized it, so this is the experiment where they realized this nonlinear optical diode, non-reciprocity realized with optical quantum optical nonlinearity. So there of course is limited. How much was it? I don't exactly remember, but it's less than 50% surely. Okay. Yeah, but people are doing a lot of experiment along these tracks. Okay, so now I will show a little more about the power spectra of this scattered light. So we can calculate again power spectra of the scattered light, and this will show for the transmitted light for a direct couple system like this monotriplet behavior, and it also was experimentally seen in the one of the early paper. Means they did of course much before when I'm doing all this. So in the one of the early paper they saw that things, but this is for side coupled two level system in the reflected power spectra, but they are related, one can show actually. Now I actually go a little quick, so I will try to quantify now this nonlinear interaction. So I'll try to say that I am talking that we create nonlinearity between photons, even for two photons, all this. So what is that amount of nonlinearity? That we can quantify using so-called Kier effect. So what is this? Let's take, we have a two-level system and we signed a coherent state beam, means a laser light here, faint laser light. So I am claiming this laser light in the power spectra, they have as we are showing here, in fact, sorry, they have nonlinear feature, inelastic scattering, all this, and also photons are becoming correlated. So what is this correlation? So that one can quantify through this refractive index intensity dependence. So this is what is called Kier effect, that when refractive index of the medium becomes intensity dependent. So let's call N is the refractive index of the medium, and N0 is the intensity independent part, and this is intensity dependent part. So then one can, if one can measure this or one can quantify N2 bar, that is the interaction in this system. So now n is proportional to phase shift, coherent phase shift. Refractive index is related to coherent phase shift of the scattered light. Now if I can even separate this coherent phase shift as a linear part which is intensity independent and nonlinear part which is intensity dependent, then I can actually quantify my nonlinearity in the problem, and that is what we do. We calculate total phase shift of the scattered light using first order coherence. So this is the calculation where we calculate first order coherence, and this part will look like transmission amplitude from which we can calculate the coherent phase shift. And then in this expression, this part is the linear, because this is which remains when I take In tends to 0. So this is linear part phi p1. So if I subtract from the total phase phi p1, I get the nonlinear part, and from there I can get the KR coefficient, which is in our calculation is giving like this. Okay, so this is the KR coefficient which gives some measure of the nonlinearity in the problem. So here I am actually showing that. So I am showing this different phase shift, total phase shift of the coherent phase shift, the linear phase shift, nonlinear phase shift, and another thing which I am going to talk next. So now this shows that this the phi p2, the nonlinear phase shift, falls as you detune the beam from the two-level transition, and that is also expected, and it has some high value. In fact, this is also experimentally seen by Chris Wilson group. They have seen not for this one but for this system. So what they have seen, they have measured cos-KR effect. So here, instead of one beam nonlinearity, you are trying to make two beams become talking to each other. When they are talking to, means when they are interacting with a common atom. So you have a three-level system. Let's take probe beams is interacting three-level ladder type structure, probe beam interacting lower two transition, and drive beam in the above transition. And we will call here again total phase shift is in the presence of drive beam, and in the absence of drive beam we will call linear phase shift, and the difference is cross-KR coefficient. So we can define Kc as cross-KR coefficient, and again we can calculate for this system first order coherence to calculate this cos-KR effect. So what I am trying to show that for ladder type structure versus two-level system, it's better to use KR effect to make nonlinearity for few photons than cos-KR effect. But it's not true for different structure, because instead of ladder, if we use lambda structure, it changes. So it depends on what kind of system you are using, that KR and cos-KR can compete. Okay, so I guess I will use 2-3 minutes and finish. So then here are some very interesting things in the direction of waveguide QED. One is ultra strong coupling regime, where one will go beyond giants coming Hamiltonian or beyond rotating wave approximation to study light matter interaction in Rabi type interaction. So this is again Chris Wilson group paper. And then there is giant atoms. So where even though you are using atom size which is much smaller than wavelength of the light, resonant light, but you couple this atom at multiple sites. So because of multiple sites coupling, you will generate, even if you start with a Markov with dipole approximation and Markov approximation, this system, you will effectively generate a non-Markovian behavior and all this. So this is a very simple way to actually go stronger coupling, effective coupling. And then of course topological waveguide, where to kind of explore the signature of topology in using light matter interaction. So these are which is going on, as you can see, but of course the biggest goal or the main goal of this field to make network, quantum networks out of these waveguides and waveguides coupled with atoms. So that surely will be the long-term goal of this field. So what I have said to you, that the generation of effective photon-photon interaction using strong light matter in coupling or strong light matter interaction for few propagating photons in the absence of any cavity or confinement along the direction of light propagation. I have discussed how to characterize such kind of effective photon-photon interaction using second order coherence Kier or cos-Kier effect. I have discussed how to study correlated light scattering in such system. I have shown nonlinear light propagation in the absence of spatial symmetry in the problem and nonlinearity. And some of the interesting problem, which at least interesting to me, is that quantification of photon-photon interaction for giant atoms. So again, giant atoms, as I'm saying, it's a non-Markovian regime beyond dipole approximation. So in there, how to even quantify this Kier coefficient is very interesting. And of course, analytical result for non-Markovian regime beyond rotating approximation are challenging, and that's why probably interesting. And finally, to study in topological waveguide correlated photon dynamics and signature of topology in light scattering, which Rupak is working, and he has seen some signature already in the last one. And again, I thank the organizer and thank you.
Really useful. I mean, very, very thorough. And thanks a lot for finishing very well in time. So we can have a couple of questions, not more, because there's an online talk coming up.
Way back in 2007, in collaboration with my Japanese collaborators from UEC, University of Electrocommunications, one Professor Hakuda was there. Their interest was in nanofiber coupled to atoms. So you're looking at this class of problems, how this atomic radiation, single photons you can generate through these fibers. So 2007, several feasible papers are there, 2 or 3 papers are there. Okay? So
No, I
the
agree.
idea.
This field is even theoretically, it started in 1980s. Okay,
I know. So my point is that when you write the waveguide mode or something, you have to include the continuous part of the spectrum also. In order to have, you don't have the continuous part, you have only the discrete part of the spectrum.
No, I am using the continuous part because that's why I'm linearizing the dispersion. And
You can do that, but that linearization dispersion doesn't mean that you are retaining the continuum part of the spectrum. There is a bound part of the spectrum of the waveguide and the continuum part.
So what do you mean by the continuum? Maybe I try to understand. What we are trying to say.
That we'll discuss later. I'll explain to you.
Okay.
Yeah, so my point is that all these things are there. That thing, of course, you need to include. And the other thing is that if you do that thing, then things are different in the sense that you need to have some, of course, you can have this Hongo-Mandel kind of single photon generation through that. And the other thing is that when you do that, it's a pretty complicated problem because that quasi-bound states will be there. And then quasi-bound states, the dynamics, to incorporate the dynamics will be very difficult. So I suggest you look at those papers. I'll give those references to you. And then several other papers are there. You just look at them. Then we can discuss. Okay?
Yeah, okay. Thanks to both speakers. Thanks to Dibyendu again. Oh, yeah.